Imagine walking into a supermarket to buy groceries, but instead of organized aisles, every single item in the store is dumped into one massive, unsorted pile in the middle of the floor. Finding a single carton of milk would take hours. By the mid-1800s, chemists faced an almost identical problem. They had successfully identified over 60 distinct elements, ranging from heavy metals like lead to invisible gases like oxygen, but they had no underlying rulebook to explain how these building blocks related to one another. Early chemistry evolved through constant iteration. Scientists were testing new organizational models, treating each failure as a necessary step toward understanding the underlying logic of matter. Organizing these elements served a greater purpose than mere aesthetics. Without a recognizable pattern, predicting chemical reactions or discovering new materials was functionally impossible. The first major attempt at a classification system arrived in 1829. A German chemist named Johann Döbereiner noticed that certain elements with similar chemical properties could be grouped into sets of three, which he called triads. Döbereiner observed a mathematical pattern within these triads. By averaging the atomic weight of the lightest and heaviest elements, like lithium and potassium, the result perfectly matches the middle element. But this neat arithmetic broke down quickly for other masses. By 1865, British chemist John Newlands proposed a new system. He arranged the known elements by increasing atomic weight and noticed a repeating cycle. Every eighth element shared similar properties with the first, leading him to propose the law of octaves, modeled after the intervals on a musical scale. The musical analogy was elegant, but it forced Newlands to compromise the actual chemistry. To keep the 8-note pattern intact, he had to cram dissimilar elements, like cobalt and nickel, into the same slot. Both of these early models tried to fit the natural world into rigid human concepts, whether it was neat sets of three or a musical octave. The atomic data needed to dictate the structure, not the other way around. Dmitri Mendeleeff approached the problem differently. He arranged the known elements by increasing atomic weights into a rigorous grid of vertical groups and horizontal periods. Looking at this chart, Mendeleeff left blank spaces for undiscovered elements. He calculated their exact properties, successfully predicting gallium years in advance. Yet, to align similar behaviors, he placed the heavier tellurium before the lighter iodine, breaking his own rule. Mendeleeff accepted these inversions to make the chemistry work. However, they revealed that atomic mass was a useful guide, but it was not the ultimate metric determining how matter was organized. The final correction arrived in 1913. A physicist named H.J. Moseley bombarded atoms with high-energy electrons and analyzed the resulting X-ray patterns. This allowed him to calculate the exact number of positive charges, the protons, inside an element's nucleus. Moseley proved that this proton count, known as the atomic number, is a much more reliable characteristic than atomic weight. When chemists swapped out weight for atomic number, the inversions like tellurium and iodine resolved perfectly into place. This discovery led to the modern periodic law. It states that the physical and chemical properties of elements are periodic functions of their atomic numbers, which in turn dictate how their electrons are configured. By prioritizing protons over mass, the sequence became consistent. This shift resolved the remaining data conflicts, resulting in a structural map where an element's position is defined by its physical composition. This chart shows exactly how that underlying logic maps out the electron structure of atoms. The distinct colored blocks correspond directly to how electrons fill their specific subshells, from the S block on the left to the P, D, and F blocks. Because of this structural layout, you can instantly predict physical traits. Take atomic radius. As you move down a vertical group, the atom's size increases because new electron shells are being added. But as you sweep left to right across a horizontal period, the increasing positive charge in the nucleus pulls the outer shells in tighter, shrinking the atom. This physical size directly dictates behavioral properties like ionization energy, the amount of energy required to strip an electron away from the atom. Smaller atoms hold on to their outer electrons with much greater nuclear force, so the energy required to remove them spikes as the atomic radius drops. The periodic table serves as a comprehensive reference. Its coordinates provide a complete profile of an element's identity and behavior without the need to memorize isolated facts for over 100 different substances.